All right, let's just dive right in. If you look at raw data, what do you see? Honestly, it's just chaos, right? It's a total storm of numbers, and at first glance, it doesn't seem to mean anything. But here's the thing, hidden inside that storm, there's an order. There's a signal just waiting for us to find it. So today, we're not just going to talk about, counting stuff. No, we are diving deep into the really rigorous mathematical tools that let us reverse engineer truth from that chaos. This right here is the absolute foundation of modern data science. So here's our game plan for today. We're going to start with the big picture, from chaos to precision. Then we'll get into the language of uncertainty, build Bayes the engine of inference, and then start modeling with random variables. After that, we'll do a deep dive on the big one, the normal distribution. And finally, we'll put it all together to see the full statistical architecture. Let's get started. Okay, section 1, from chaos to precision. Let's do this. The whole point of data science, our core mission, is to take all that uncertainty and forge it into precision. We're taking abstract ideas and making them concrete, actionable, and mathematically solid. And this image, this pretty much perfectly maps out that journey. You see, we start over here with the pure logic of probability theory. Then, we use this amazing bridge called random variables to translate real-world outcomes into numbers we can actually work with. And from there, we build out our models, distributions, which is what finally lets us do the real, rigorous measurement and analysis. All right, on to section 2, the language of uncertainty. So, look, before we can jump in and start building all these cool, sophisticated models, we gotta get on the same page. We need to establish a shared language and, more importantly, a set of rules that are completely unbreakable. This stuff is the bedrock of everything that comes next. So what is this bedrock I'm talking about? Well, it all starts with the sample space. Super simple concept. It's just the set of every single possible outcome. Think about rolling a die. The sample space is just the numbers 1 through 6. Now, this whole space is governed by just 3 simple but incredibly powerful rules. We call them the Kolmogorov axioms. Axiom 1, probability can't be negative. Makes sense. Axiom 2, the total probability of everything that could possibly happen has to equal 1. Again, totally logical. And axiom 3, if you have events that can't happen at the same time, their combined probability is just the sum of their individual probabilities. That's it. Every single complex theorem we're going to talk about today, it all flows from just these 3 fundamental ideas. Okay, section 3, Bayes, the engine of inference. So, we've got the rules of the road down. Now, let's build the engine. This is the mechanism that lets us actually learn from data and update how we see the world. The first big component we need for this engine is conditional probability, and the intuition here is just so powerful. Think about it. When you get new information, your whole universe of possibilities just shrinks. You're not asking, hey, what's the probability of A happening out in the wild anymore? Now you're asking, what's the probability of A given that I know for a fact that B has already happened? We're now playing in a much smaller sandbox, the universe of B, and we just want to know what fraction of that new, smaller universe also includes A. And that brings us to maybe the most important question in all of statistics. How do we formally, mathematically update our beliefs when we see new evidence? How do we actually quantify that shift in our understanding? And the answer is the beautiful, elegant Bayes theorem. This is the engine of statistical inference. It gives us a formal way to take our prior beliefs, combine them with new evidence, what we call the likelihood, and come out with an updated posterior belief. But here's the real magic. It lets us flip the script on cause and effect. Instead of just figuring out the probability of an effect given a cause, which is often easy, we can now infer the probability of the cause given that we've seen the effect. This is the absolute core of scientific reasoning. It's how your spam filter learns, it's how medical diagnostic tools get better, it's everything. Okay, let's move on. Section 4, modeling with random variables. Now, talking about abstract things like event A and event B is great for theory, but if we want to do real math, calculate a mean, a variance, we have to translate these real-world outcomes into actual numbers. And that is where the random variable comes into play. It's a really essential concept. It's basically just a function, we usually call it a capital X, that maps the outcomes from our sample space, like rolling a die, onto the real number line. It's the critical bridge that lets us take all the powerful tools of calculus and algebra and apply them to the world of probability. Now, these random variables basically come in 2 main flavors. On one hand, you have discrete variables. These have countable outcomes, right? Like the number of heads you get in 3 coin flips. To analyze these, we use something called a probability mass function, or PMF, and a lot of summation. On the other hand, you have continuous variables. These guys have uncountable outcomes, like someone's exact height or the temperature. For them, we need a probability density function, a PDF, and the tools of integration. And I really need to stop and emphasize something critical about those continuous variables. The value of the PDF at any specific point is not a probability. Why? Because in a continuous world, the chances of hitting one single exact value, like a temperature of exactly 20.12345 degrees, is basically zero. It's infinitesimally small. So probability only makes sense over an interval. And how do we calculate it? We integrate the density function over that interval. Or, to put it simply, we find the area under the curve. So, with that in mind, what kind of models can we actually build? Well, for discrete events, we have an awesome toolkit. The Bernoulli distribution is for a single success/failure trial, like one coin flip. The binomial builds on that. It models the number of successes in a bunch of trials. And then there's the Poisson, which is perfect for modeling the count of rare events over a set period of time, like how many calls a call center gets in an hour. And we have a similar set of workhorses for continuous data. The uniform distribution is what you use when anything in a range is equally likely. The exponential distribution is key for modeling the time between events, like wait times. And then there's the normal or Gaussian distribution, the undisputed champion for modeling all sorts of things, from errors and noise to countless natural phenomena. You know what? Let's actually pause here and do a proper deep dive into that last one. Section 5, the normal distribution. Because honestly, this is, without a doubt, the single most important and widespread distribution in all of statistics. So why? Why is the normal distribution, this bell curve, so incredibly common? It's not a coincidence. It's because of a concept that is the absolute climax of probability theory, the Central Limit Theorem. And I'm not exaggerating when I say this theorem is the miracle that makes modern statistics possible. What it says is, if you take a large enough number of samples from any distribution, I don't care how weird it is, and you average them out, the distribution of those averages will start to look like a normal distribution. It's this magical bridge between pure theory and the messy reality of our data. It's why the bell curve just shows up everywhere. And because of this, we get a fantastic rule of thumb, the empirical rule. So this rule tells us that for any process that follows a normal distribution, about 68% of your data will fall within one standard deviation of the average. About 95% will be within two. And a truly astonishing 99.7%, almost everything, will fall within just 3 standard deviations. This is huge. It gives us a way to quantify just how unusual any single observation is by calculating its z-score, which is just how many standard deviations it is away from the mean. It's a super powerful way to standardize and compare data, even if they come from different normal distributions. Okay, wow, we've assembled a lot of pieces here. So let's take a step back, zoom out, and see how they all fit together to form the complete analytical framework we use as data scientists. Section 6. The full statistical architecture. And this right here, this is the whole shebang. It shows the complete architecture. We start at the bottom with the foundations of probability. We use those to build up the idea of random variables. Then we model those variables with specific distributions. And finally, we analyze them using different tools. But why do we do all this? This whole structure serves one single purpose. It gets us ready for the main event, statistical inference. So what we've just done is construct our entire foundational toolkit. And I want to be clear, these aren't just abstract academic concepts. No, these are the practical, hands-on instruments we use to estimate the hidden parameters of the world, all from our limited, messy, noisy data. This is it. This is the art and science of reverse engineering truth from data. We've just walked through the entire schematic. You now have the architecture to go out there and find order in the chaos. So the only question left is, what truth are you going to go find first?